Thank you so much for joining this seminar about the power of GPU in scientific computers. And I hope this seminar will be very beneficial for you, especially you are doing computing in a different platform and you are using GPU or CUDA programming to solve many problems. So I hope this seminar will help you in your project. Without wasting time, so we'll gonna talk about the parallel computing as general and how it is very useful in scientific computing, and also we'll talk about the uh, processor components and performance because those are the important components in any computing. And then we will talk about the parallelism and parallel system architecture as general because there are many parallel system architecture. So knowing it really is very important and will help you to use which architectures that work for your problem. And then we will talk about the GPU or graphical processing units and its architecture. And after that, we'll talk about the CUDA programming because this is the framework or the programming libraries that are used to use GPU in parallel computing. And then we will talk about the general flow of GPU programming and about how to use Python library because most of the time we're using CUDA with C++ or Fortran. And Python language is the library used in Python library and new. So we'll give you some examples on how to use Python as well with in GPU programming. Then of course we'll discuss some examples. And these examples will give you idea about how you can use GPU. And in fact, there are many applications for the GPU or graphical processing unit, and it really helps us to solve many problems. In the past, solving this problem was almost impossible, like weather forecasting, for examples. And in weather forecastings, so just imagine that if we need to measure, the temperature on the atmosphere, so we need to divide large space into grids, and then we need to compute or use differential equation in this grid. That means we will use like many cores, computer cores, maybe millions to solve this problem. Before the GPU getting this number of cores was impossible, but right now it's possible. All we need just GPUs that with that millions, that number of cores, or some GPUs with number of cores, they can solve this problem by running differential equation or thread into each grid and get the solution. Also, the GPU is used in image processing like filtering and edge detection. And here, depend on the image itself. So we need each program working on pixel. So the same program will process a pixel. So if such a problem solved sequentially, that will take a long time, but using different eye cores that work simultaneously at the same time, so this problem will be solved in a very short period of time. And also we're using GPU in machine learning. I will give you some examples in machine learning, like there are some libraries that they're using to solve this machine learning. And also we're using them in many problems, like, the simulations and molecular dynamic simulations as well, and in image rendering, in 3D visualizations, and so on. So there are many applications uh, in which you are using GPU. So GPU really become very important component. But before we go and talk about the GPU, let's give you idea about the processor as general. And when we say processor, it can be like CPU or central processing unit or GPU. The idea of processor is still the same, but architecture may be different. And processor itself, because it process information, and that information is either arithmetic or logical, or logical operation. So the processor itself, in its simple way, consists of control units that which you control all operations performed by the processing unit, and arithmetic and logical units. And of course, this is the unit that does the arithmetic operations and logical operations. So any arithmetic operation like addition, subtractions, multiplication, divisions, or anything like that. So this is the arithmetic unit will do that, and at the same time also the logic like and or not, and this which you create the different computing depend on these operation. And then internal memory, and by internal memory we mean the registers and cache, and those very important because when we process any information, we need to store that in area, then so they can be used by processor or used by the arithmetic and logical units. And the movement, the traffic between this area, between memory and this is very important, because if that depends on the latency, if it takes a long time, that will affect the processing. If it takes a shorter time, it will be processing. So there is a different mechanism to reduce the speed or to reduce the latency. That means the transfer of information from internal memory like cache or register to the other units. So this is also some essential part, and scientists who are developing computing system, sometimes they are focused on these to improve the computing system, because by optimizing this will reduce the latency. And of course, after that we have the main memory, and we have the permanent storage, and we are dealing with that in daily basis. When we are using computers, we know that the information will move to the memory for any kind of processing, and if we need to store anything, we will store them in permanent memory. And also we know about the input devices like keyboard and mouse and scanner, and output devices that like console and printers and so on. So when we talk about this, also we have to talk about the performance of computing system, and we need four metrics that measure the performance. And one of these, like clock speed, which measure in like gigahertz, or the number of cycles per second, and also latency, as we said, this is the time taken for a specific operation to be completed. Flop, which is floating point per floating operation per second, also is very important, because especially in scientific computing, we are the speed also can be measured by like how many floating operation can be performed in a second. And throughput as well. That means like the bandwidth, or like the amount of data that can be processed per second, and bandwidth, the maximum size of the amount of data that can be transferred in a second. Also, these are metrics that we can focus on. And it is also important to know about the serial computing and parallel computing. Serial computing is when we have instructions, because the program itself consists from constructions, and when we do that constructions in sequential, that means step by step, it will take a long time. But if it is possible to do this program, instead of be sequential, to divide it into tasks, and then doing this task in simultaneously, that it will cut in the execution time. So this is the difference between the sequential. Sequential means that the program will be executed sequentially, step by step. When the first step ends, the second step will begin. They cannot be executed simultaneously. In parallel processing, the problem will be split into tasks, and those tasks will be executed simultaneously. That means at the same time in parallel, and that contribute to cut the execution time. And there are different kind of once we talk about the parallel system, there are two major architecture for parallel system. One is shared memory architecture, and the second one is distributed memory architecture. In shared memory architectures, here we have several CPUs, but all the CPUs share a common memory. And here we are using a specific programs. We are using program like pthread, and pthread is library used under C++ and Fortran, and it is built in the operating system that can be used in any programming language, but most of the time they are used by Python and C++. And OpenMP, also it is C library as well. Also we use it for shared memory. For distributed memory architecture, and here we have multiple computers, and each computer is completely independent. And by independent means that it has all the components, computing components like memory, cache, and everything. But those independent computers are connected with interconnect and interconnect, and then we need the programming languages that can use these different worker or different computer to parallelize, to do things in parallel. So we call this distributed memory architecture, and the program that we are using for this purpose is MPI, or message passing interface. So these two types of parallel system, but also we have to talk about the type of parallelism itself. Okay, so what kind of parallelism? And there are two parallelism, either task parallelism or data parallelism. In case of task parallelism, we will parallelize the task itself. So we have different tasks, and those different tasks will be distributed among workers or CPUs, and they will be executed simultaneously. In case of data parallelism, here we need to divide or split the data into chunks and then to process it simultaneously. So there are different strategies, but most of the time we may use both strategy at the same time, but these are the type of parallelism that we are using. So now we'll come to the graphical processing units. We have already talked about two architectures for parallel system. One is shared memory. The second one is distributed um, memory system. But now we have a third method, which is graphical processing units, and this is just a chip. And inside chip, we will find many core or many processors. So that means we have multiple processors, and we can use these multiple processors to doing things in parallel. So this is a new technology, and it keep developing since 1990, and before it was just for graphic rendering and gaming, but now we are using it for scientific computing and deep learning and many applications. And about the GPUs, there are two kind of GPUs: integrated GPUs and dedicated GPUs. Integrated GPUs, this is GPU integrated in the motherboard or motherboard of the computer. So that means it's integrated and they share memory with the CPU. By the way, GPU cannot be completely independent. That means there's no computer that working with all the GPU. It always, there's a kind of relation or link between GPU and CPU. Okay, so why we call the CPU as a host and GPU as a device. Generally, there are two kind of CPUs. One is integrated in the motherboard, and it's shared memory with CPU. That means it doesn't have independent memory. And dedicated GPU, and this is completely different GPUs in each different card or PCB, and it has its own memory and architecture. And most of the time, we are using dedicated CPUs in computing. So our focus will be only on the dedicated GPU, because this is the GPU that we are using. And about the GPU consists of different core or different CPUs, and these CPU, we call them, can be divided into blocks, and these blocks we are calling streaming multiprocessor, and all these they share same memory. So they share memory, and there may be multiple multiprocessor depend on the architectures of GPU, because there are many GPUs. And then all these multiprocessor also, they share a common memory. We call them data cache. And all these data cache also, they can write to global memory. So global memory will be accessed to all threads or all blocks, but shared memory access only to a multi-processing. And this architecture, by the way, is very important, and it is very determinant to computing at the same time, because we say that always there is there is always there is a link between the GPU and CPU. The information must be in the CPU first. After that, they will be transferred or copied to GPU, where they can be simultaneously. They can be processed simultaneously, and after that they copy the result back to back to the CPU. This is how the relation between CPU and GPU works all the time, and the GPU cannot work dependently. So this is just an example of architectures of GPU and GTX 980 or GeForce, NVIDIA GeForce. There are other companies as well, like Intel and other companies give you, but the most used one is NVIDIA company, and it has many brand. One of the series, this is just one series, like GeForce GTX 980, and uh, and each one has different architecture, but the idea is the same. They have graphic processing cluster and streaming multiprocessors, and they have the shared memory and part common memory that communicate with the CPUs, and but the architecture is the same like the ones that we discussed before. So they are different for NVIDIA. GPUs are architectures are different architecture. In fact, they are different brand of GPUs and for different purposes at the same time, and some of them for gaming and video rendering, 3D modeling, some of them for machine learning, some of them for scientific computing, and so on. So before you choose your GPU, you need to think about what you're going to do. If you are doing computing, you have to use the ones that are optimized for computing. And if you need for image rendering, then you will use the GPUs that optimize for image rendering. But there are many, and always we have to think about like not only the architecture, but we have to check the number of cores, because each one has a specific number of cores or CPUs. And if you see here, Volta Quadro GV100, and this is the one that we have. It has 5,120 cores, and it has 32 gigabytes, and we can use it for deep learning and scientific computing and visualization as well. So always look to like the number of cores, because that it will tell you like how many operations that can be processed simultaneously. Again, also there's like GeForce series NVIDIA GPUs, and these they're using most of the time for gaming and for rendering and so on. Also, you can look for cores and how many cores you are using and memory, because those are important factor in any computing process. So the number of cores and the memory size, and so these are the major determinant of the good GPU. So now we'll talk about the CUDA. And CUDA, this is CUDA. So this is like a platform or a library for using the GPUs simultaneously, or to use the parallel system in GPUs. And in CUDA, this is like building software in NVIDIA GPU, and it consists of some part. Consists of CUDA toolkits, which include runtime, libraries, and tools. And the second is drivers components, which include the CUDA user mode driver and GPU kernel model driver and so on. So these two portions, toolkits components and driver components, are the components that form or consist that form the CUDA. So once the GPU is CUDA enabled, then there must be those components to make it possible to use it. About the CUDA toolkit components, they are like different tools or different libraries, because the libraries of CUDA toolkits that include like CUDA runtimes and application programming interface and NVCC, and this is the compiler, and CUDA library like cuPlast is for basic linear algebra subprograms, and CUFFT is for fast Fourier transform, and CU is sparse. This is for standard algorithm for sparse matrices. CUDA profiler, and also and CUDA. And this library is for machine learning, for neural network, used by TensorFlow and PyTorch. And also there are other libraries as well, but these libraries, we call them CUDA toolkits component, and really they are very important. So there is a command, if we once we get the computers, and if we want to know that the CUDA toolkit installed in the system, then we need to run this command NVIDIA-SMI. Once we run it, we will get a result, and that result will tell us if we get, if we get output, that means the program is very, that means the code is already enabled. If we didn't get any output, that means we need to, there is something wrong, and CUDA is not available, or maybe the GPU itself is not available, or maybe there is no, the driver is not installed, or the CUDA toolkits is not installed in the system. So the first step we have to take by running this command on the command line, and we should get a output, and this is the output for a NVIDIA SMI. So what this output tells us, so this, if you can see, this actually can be split into two tables. One, it tells us about the GPU information. The second one about the active process that use these GPUs. And about the GPU information will tell us about the GPU name, the GPU itself, like brand, and the name of the GPU, and temperature of the GPU, and usage, and in fact they give us like very useful information. And the most used information is the ones that we circle here, like the temperature is 40, and it shouldn't be it should be around this, that means it's fine, and it shouldn't get to like 95, that means the temperature is very high and should be reduced. And performance P2, this will show you what performance it does, and there is like a different key like B1, 2, 3, 4, and so on. So like this means that this performance is suitable for computing. And here this circuit will show you like how many of the memory has been used by the process. So it will show you that. And again, here the GPU utilization, no program or no process using the GPU now, because this is 0%. So if it's being used like 100%, it will show here. So this will show you like how the percentage, how much of the GPU have been used. So it gives you really good information. The second table is show you the active process that use the GPU. And if you see here, we have some default processes, because this they are used by the just by the interface, by the graphical user interface. So nothing computing is happening here. And this column is specifically telling you about that. It tells you that this the process that running now or use the GPU are graphic. If anyone is C, that will be computing. So the second command, very important command, the compiler itself, because you may need to write code in C++. So you need to compile it. You will use a compiler, CUDA compiler, and it is MVCC MVCC. And if you want to check whether this compile installed or not, you can run mvcc dash version. It will tell you about the version of the compiler, and we use this when you write code in CUDA code in C++, then you can use this command to compile your program. So this is generally about the CUDA programming concept. We say that always there is a relationship between the CPU and GPU. So why CPU we call it host and GPU we call it device, and there is kind of link because most of the work first begin in CPU, and the parallel work that we need to execute it in the GPU, it will be transferred to the GPU where it can be executed in parallel or simultaneously. And the kind or the model of programming in GPU, we call it SIMD, or it is single instruction, multiple data. That means a single program, but there will be multiple data on it. So this is the model. This is the model of programming or parallelism that take place in the GPU or can be done by CUDA programming. So there will be a single task, but single instruction, but will be multiple data. And when we talk about the programming concept, it's very important to understand the programming, how the organization of how we use these cores. And cores we use what we call it CUDA threads, and each core in the GPU executes simultaneously execute CUDA thread. So generally, programmatically, we can organize this different or thread into we can create a big grid, and inside big grid will be blocks. So each block there will be a specific number of threads, and grid and thread can be 2-dimension, can be 1-dimension, 2-dimension, or can be 3 dimensions. So we can organize the thread in a different format. So that means the thread can be organized into blocks, and blocks can be 1-dimension, 2-dimension, or 3-dimension. That depends on the problem that we are dealing with. In fact, the organization of this thread dictated by the data structure that we are dealing with. So Y, they will be like X, Y, Z. That means 3-dimension for block, and at the same time also for grid will be can be 1-dimension, 2-dimension, or 3-dimension. And if you see in this figure here, we have thread, and these thread. So these, in fact, this thread and this thread, each of this thread in a block. So here we have some blocks, and thread actually divided into blocks, and a block inside a grid. And we can say this when the grid itself is 1-dimension, because it's just 1-dimension. It's 1-dimension grid. That means the number of blocks here, all of them, they found in x-axis, right? So we call them out here. There is much explanation for this. There is a built-in data type, dim3, and dim3 here we can use this to organize the thread. And dim, we can define, we have to declare grid size and block size to shape or date or the thread in a specific shape. And for example, here we use dim grid size to 1 That means this in fact this 1-dimension. Okay, this 1-dimension, and here we have only 2 only we have 2 blocks, because this is a grid, we have 2 blocks. But when we come to the block here, we have 4, 3, 1. Okay, so here that means we have two-dimensional block, 4 and 3. That means x axis we have 4, and we have 3 in y axis. That means it is 2 dimension. So if we need to compute the total number of threads, then we need to multiply 2 by 4 by 3, and we have 24 threads. So this is the total number of threads. And also we can do that in 3D as well, as you see that. That depends, as we said, this dictated by the dictated by the number of dictated by the data structures that we have. Because most of the time, if you are dealing with 2 dimension, with 1 dimension problem like vector multiplication, then we will use 1 dimension. If you are dealing with the 2 dimension like linear algebra, then we use 2 dimension. If we are dealing with image processing, which require data structure to be in 3D, then we will use 3D structure. So the structure of data dictates the organization of thread in 1 dimension, 2 dimension, or 3 dimension. But we have to put in our minds that always there is a total number, the total number of thread in a block. Most of the nowadays GPUs, they take 1024 thread per block. You cannot go beyond that. Okay, you will get an error. So some of them, they have the number of this, maybe but most of them, and you have to check the specification of the GPU before you use it to know what is the maximum number of threads that can be organized in a block. But most of them, they 1024 thread. And so also there are some CUDA built-in variable. We are using them, and that will help us, to do computing, and we use them in CUDA programming, like grid dim, which represents the dimension of the grid. Block dim represent the dimension of block, and block IDX give us the index of block and thread index. So these built-in variables are really very important, and because like dimension, we have X, Y, Z. So each one of these, it can take a different value. If we need we can access, and block index and thread index. Also, we use them to determine the index of during our operation. Because most of the time when we are doing computing, we need to know the index of that thread to do some kind of computing or do any kind of communication to get the results. Or so knowing the index of thread is essential part in GPU computing. Of course, we are using C++ or Fortran. Most people actually, they're using C++ because this is the very well established language. And in CUDA programming, when we use what we call CUDA kernel. And CUDA kernel is a function just like C or C++ functions. The only difference is there are few keywords like underscore global, underscore. So it begins with this keyword, and then void, and then the function name or the kernel number, and here whatever the argument, we can place the argument here, and then this is the body of the function. So similar is just like C or C++ functions. The only difference is the underscore global underscore void, and that is it. So this is how it looks, because once the compiler found this, That means immediately it will know this function must be executed in the GPU and not in the CPU. So we know that. So we have to know this is the general form of the kernel, and whenever we need to run any instructions or program in the GPU, we have to use kernel, and this kernel or function, it will be executed simultaneously in the GPU. So kernel, of course, is a function, but it must be run from inside the main function of the C or C++, because it cannot work independently. It's as we said, the relationship between the GPU and CPU always is kind of relation, and the GPU cannot work independently, but they must be together. So the function or the kernel, it must be executed from inside the main function of C++, and the process of calling the function here, we call it kernel launch. So the kernel launch means just like running the function from inside the main function of C++. So first we need to configure our thread. As we talk and discuss that, we say that they must be organized into whatever dimension dictated by the data structure. It can be one dimensional or two-dimensional or three-dimensional, and so we call these thread or configuration. And after that, what we do, we need to launch the kernel, and we can, because if you have like multiple devices or multiple GPUs, of course they will be numbered from 0, 1, 2, 3. You can select the GPUs that you want to use, and CUDA set device 0. That means we'll use the first one, or 0, and this is how to run the kernel, or how to call a function. And here we call it how to launch a kernel, and the name of the kernel is already my kernel. This is the kernel that we have to define it outside this function, and then we will find this 3 angle bracket, and then we have to put the grid size and block size already declared here, and we determine whether these size are 1 dimension, 2 dimension, or 3 dimension. Based on that, we have to define the grid size and block size here between these, and after that, if there are any argument, we have to provide them here. This is the general format of kernel, run kernel. So once we once we compile this program, and the CPU finds the instructions, this is kernel launch, it will send this instruction to the GPU, and it will be executed there. So anything here after that, it will be executed in the CPU, but only the kernel will be executed in the GPU. And so the general flow of the GPU programming, first we need to identify the computational task and decomposition, and here definitely we are working with a specific problem, and that might be optimization, might be molecular dynamics, or any kind of computing problems. We need to think about how to parallelize it, how to decompose it. So this will be solved by the user himself, and once he did that, then after that he can write kernels or the functions that do that process that task or that data, and the kernel can be kernel for any task like differential equation or multiplication or addition or any kind of problem that you need to parallelize it. You need to execute it simultaneously in different code at the same time. Then you create that kernel, because that kernel will be executed in the GPU. So once you create that, then you have your data. Of course, the data first must be in the CPU. You cannot just put your data directly to the GPU. No, first must be in the CPUs, and if you need to allocate area in the memory, then you can use the C function, malloc, memory allocation, to allocate area. Like if you have matrix or vectors or anything, you can allocate area there, memory there, and then you need to and at the same time also you need to allocate these to keep them there, because their location in the memory will be known. And we use pointers, and most of the time we are dealing with pointers in this kind of programming, because we can take pointer the address of the memory instead of the value. So after that, we transfer that data already in the CPU, from the CPU or from the host to the device, and device is the GPU. So that means first we have to put the data in the CPU, and once it is there, we need to process it. We need to transfer that data from the CPU to the GPU, or from the host to the device. And here we use a function, CUDA mem copy. Okay, and the first one is from this will be from the device, and then we copy to the host, and the size of the data that we need to transfer it, and this key, it will show you the it shows the direction. So it's from memory of the CPU to the device. Then we need to launch the GPU, and by launching the GPU, that means we run the function or the kernel in the GPU, and of course we run it simultaneously based on the information that we provided provided when we configure the threads. And once we get the result, then we need to transfer the data back from GPU to CPU, and again we are using the same function that we used before, which is CUDA mem. The only difference here, we are using different direction here, because this direction, it tells us from device to the host. Then finally, we have to free the CPU and GPU memory, because we allocate memory area in the memory, and if we didn't erase them, that means we'll create what we call it like garbage memory, or garbage data will be there, so it must be erased, it must be deleted before we end our programming. So this is the general flow of GPU programming, and after that there are many examples that we will try next time to discuss them. So now you know how the GPU architecture, and CUDA programming, and the general flow of CUDA programming. So the next time we will discuss, we're not going to discuss, but we will do practically how, we'll discuss some example. Practically we have the code, and we see how we can run this, how we execute kernel, and how we can use CUDA programming to solve many problems, like machine learning, for example, how to do optimizations and image rendering.